is B06211046. Today, I'm going to present the introduction of this assembly. First of all, to test the power supply circuit, we need to use key component of the power supply, included transformers, rectifier, filter, voltage regulator, and protection circuit. Understanding the functions and components of the power supply is crucial for designing and operating electronic systems effectively. What is a power supply? A power supply is an electronic circuit designed to provide various AC and DC voltage for the experiment operation. We do this because as the project manager of Sungrow Power Supply Company, the task is to engage the design team in testing the power supply circuit and applying the engineering concept. So, in testing the power supply circuit, we need to use key component. Secondly, component in the power supply. As I said, transformers, the function of transformers is step up or step down voltage or current, provides isolation. The second one is rectifier. The function for rectifier is changes AC to pulsation, half wave or full wave. Third one is filters. Filters out pulsation from half wave or full wave to make the purer. Fourth one is voltage regulator. It provides very exact voltage, will not vary. Next is methodology. The first thing of the methodology is detailed specification of power supply component, which is transformers, diode, capacitor, AC source, and ground. The second one is design assumption and calculation. These assumptions are aligned with the desired fixed DC voltage output for various electronic appliances. Third one is measurement technique using multism. Multimeter and oscilloscope perform measurement waveform, analyzed in multism emphasizing the accuracy of voltage and current measurement. The fourth one is validation and final output. An output voltage of 9.595 volt for the positive output and negative 9.645 volt for the negative output. The voltage at the AC source, initially 240 VRMS, is successfully transformed into the desired output. Thank you.
The selection of component value is crucial for accurate and trustworthy result in power supply circuit simulation using multism. It involves choosing a transformer with appropriate voltage rating, diode with adequate voltage and current rating for rectification, and electrolytic capacitor with the necessary computations for filtering without exceeding the predicted voltage across them. This ensures the desired load is met and the simulation results are reliable.
Assalamualaikum and hi everyone, my name is Nurul Kismin Raza. I want to present about the construct a simulation circuit from a schematic. So I show you the multism set B we choose. This is a AC power resource. It's an electrical system that generates and deliver electrical energy with the direction for the current period the servers. This the specific the frequency, especially 15 Hz, and is the characteristic by a sinusoidal waveform. AC power resources are widely used in the households, industry, and commercial application due to their ability to efficiently transmit electricity over long distances. So when the AC circuit in the model system and go this power and go the tapered circuit that full burst rectifier is a circuit used in the power supply to convert AC, and the utilized transformers with a center tap on the secondary winding. During the positive half the circuit of the AC, we have the current flow through the one half of the winding, producing and the positive voltage across the load. In the negative left circuit, current flow through the other left carrying and the negative voltage. Then this is a diode. The diode is a manipulator. It develops with the two terminal design and to allow the electric circuit to flow in the one direction with the hindering if the flow in the opposite direction. So the function is less the in rectification, converting alternating current AC, and by facilitate the current passes during the positive half the circuit and the negative circuit. Then we go the capacitor. This is a capacitor. The capacitor is the key electronic component that stores and releases electrical energy in the current. So capacitor have a diverse function in the electronic circuit, such as the electric storage, voltage smoothing, and the signal filtering. Then we go the voltage regulator. Is an essential electronic component that ensure a stable output voltage in the current circuit. This is the input voltage fluctuation or the change in the load direction. So the voltage is available in the line, and the switches type using the different machinings to adjust and the regulated voltage. They play and the crucial role in the maintaining the reliability and long lasting of the electronic system. Then we go this This is a earth ground. Earth ground is a critical component in the electric system, providing a reference point for the voltage and the safe part for the electrical current to flow into the ground in the case of the flood. So these are the safe propagation difference and protecting equipment and individual from electrical shock. Then this is perimeter is the vestige the electronic measuring tools used for the testing in the electrical and electronic application. It combined to function like the measuring voltage, current, and is extended with the display from a character readings. The equipment is the broadest is they can be connected to current or component. Model the multimeter it offer advantage feature and can see the multimeter is so the function simulator is the real words to allow using to make sure the electrical parameter is like such as the voltage is very similar the currents. Next, the last one is this is a oscilloscope is a vector electronic testing tools using the uses and analysis voltage signal over time. So this by connecting a broader into different point and if the current user can operate make sure the signal characteristic like amplitude and frequency. So look like this. The characteristic presented at the display is voltage signal is shown one graphically over time where the use overlay connected to specific. The point the electronic the current, the power over the voltage filtration into the electrical signal and the real-time paragraph to the display and the characteristic such as the frequency. That's all from me. Thank you.
This is the multisum simulation circuit that was created from a schematic. Now we are going to test the functionality of the simulation circuit and see the result measurements together. Firstly, we should connect the measurement tools like oscilloscope and multimeter to the circuit. Here is the simulation circuit that has been connected with those measurement tools. The first oscilloscope is to measure the AC source voltage. It has two channels, which is channel A and channel B. Positive probe of channel A is connected to positive side of AC source and the negative probe is connected to the negative side of AC source. While the positive probe of channel B is connected to the transformer's positive side and the negative probe is connected to the negative side, which is the center of transformer. The second oscilloscope is to measure the final DC output. The positive probe of channel A is connected near the PR4 and the negative probe is connected to the middle wire that is negative side. While the positive probe of channel B is connected near the PR7 and the negative probe is connected to the same point where the negative probe of channel A was connected. Next, the first two multimeters are connected to measure both the positive and negative voltage value of final output. The positive probe of multimeter 1 and multimeter 2 is connected near the C3 and C7 respectively. Then, the negative probe of both multimeter is connected to the middle wire as it is the negative side. The next two multimeters are connected to measure both the positive and negative voltage value of two IC regulators, which is LM7809CT and LM7909CT. The positive probe of multimeter 3 and multimeter 4 is connected near the C1 and C5 respectively. Then, the negative probe of both multimeter is connected to the middle wire as it is the negative side. Finally, we can click the current and voltage symbol on top of the toolbar and place it at places that we want to measure the current and voltage of those components like diode, capacitor and so on. After all set, we can click the run button on the top and make it run for few seconds. Then we stop it. Now we can see the readings from each and every measurement tools that we inserted. This is the reading of oscilloscope 1. Channel A shows a sine wave for the AC source. The peak voltage of the sine wave is approximately 339.4 volt as shown by the reading on the oscilloscope display, while channel B waveform is much smaller in amplitude than the sine wave of channel A. The peak voltage of it is 33.9 volt. The value should be in root mean square as it is AC source. For a sine wave, the RMS voltage is equal to the peak voltage divided by the square root of 2. In this case, the RMS voltage for channel A is about 239.1 volt and the RMS voltage for channel B is about 23.8 volt. Let's see the reading for the second oscilloscope. The oscilloscope reading is showing the voltage measurement for the final DC output. Channel A exhibits a distinctive waveform characterized by a flat line rather than a sinusoidal pattern, indicating a continuous direct current voltage of 9.594 volts. Channel B presents a waveform that, like channel A, manifests a flat line on the display but with a negative polarity which is negative 9.643 volts. As for the multimeter's reading, the first two multimeter readings show that the output voltage at the ground is 9.595 volt for the positive output and negative 9.643 volt for the negative output. This means the functionality of the completed power supply circuit has been validated by using multisum simulation software. The LM7809 is a positive voltage regulator that outputs a fixed voltage of 9 volt. The LM7909 is a negative voltage regulator that that outputs a fixed voltage of -9 volt. The multimeter in the figure is measuring the voltage across the output capacitor of the LM7809 regulator. The reading on the multimeter shows that the output voltage is 33.172 volt. The voltage and current in the LM7909 regulator are likely to be similar to the voltage and current in the LM7809 regulator. However, the negative voltage output of the LM7909, that is negative 33.172 volt, means that the current will flow in the opposite direction. Finally, the yellow boxes shows the current and voltage for the components in the circuit. For example, the voltage and current after the diode D1 is 33.2 volt and negative 12.8 Na respectively. The measurement for other component like capacitor is shown in the yellow boxes too.
A switch mode power supply (SMPS) is a sophisticated and efficient power conversion technology used in various electronic devices and applications. It operates by rapidly switching input voltage on and off at higher frequency, unlike standard linear power supply, which manage voltage by dissipating surplus energy as heat. The SMPS operates through a high-frequency switch, a transformer, and a filtering and rectifying process, providing a steady direct current output. The output voltage is regulated via a feedback control loop, ensuring exact and consistent output voltage even when input voltage or load conditions vary. SMPS technology offers several topologies, including buck converting machine, converter booster, and converter for bucks. Its advantages include increased productivity, smaller size and weight, numerous applications, increased regulator and stability, lower heat generation, and greater power density. SMPS minimize energy loss by rapidly switching between on and off state, reducing power dissipation and increased energy efficiency. Its compact design allows for smaller and lighter power supply unit, especially in limited space. SMPS also ensure power supply stability by adjusting output voltage even when input condition or load change. It also creates less heat during operation than linear power supply, resulting in a cooler and more energy efficient system. Moreover, SMPS efficiency and compact design lead to increased power density, allowing more power to be delivered in a small space. Overall, SMPS technology is a popular choice in modern electronic systems for energy savings and performance improvement.
Hi everyone, my name is Muhammad Agil BENG3013. Then my metric number is B06211034F. For my part, I will be presenting about the advantage and disadvantage of the proposed solution. For advantage, there are 6 main points, and disadvantage also have 6 points that I put in the slide. So for advantage, the proposed bipolar power supply design shown brightly in the realm of electronics, embodying simplicity, efficiency, adaptability, control, and affordability. Its straightforward construction aids troubleshooting, while its efficiency minimizes power loss, crucial for portable device. Its adaptability suits various applications, and voltage regulator ensures stability. Additionally, its cost effectiveness make it an ideal choice for project with budget constraint, educational endeavors, and cost sensitivity commercial applications. In this symphony of electronic undertaking, this design proved to be harmonious and practical compositions. Now I will be explaining about the disadvantage. While the proposed bipolar power supply design offer notable advantage, its limitation must be acknowledged. Concerns include low output current capacity, risking component failure and safety hazard. Transformer-induced noise pose challenge for sensitive application, necessitating trade-off for noise reductions. Limited mobility due to reliance on main power effect versatility, and the restrict voltage adjustment range may not meet precise requirements. Additionally, reliance on easily accessible components may pose challenge for specialized projects. Acknowledging this drawback is essential for informed decision-making aligned with specific needs and prioritized in the dynamic realm of electronics. 4-part eco-friendly component sustainability assessment. Transforming the proposed bipolar power supply into an environmental champion involves selecting eco-friendly components with spring toroidal transformer, sunlit silicon carbide diode, and resilient capacitors. Picture voltage regulators in energy efficiency, sleep and circuit board fashioned from natural fibers. Yet, a robust sustainability assessment is the fertile soil for true friendliness. Life cycle analysis guide us through environmental impact, energy efficiency, vigilance, ethical procurement, recycle options, and dignify end-of-life practice. This collaborative effort across the supply chains with a tapestry of responsibility, promising a harmonious and sustainability feature in electronics.
Going to present about the end-of-life consideration, the implementation strategy, and the cost-benefit analysis. So first of all, as we envision the implementation of SMPS technology, it is imperative to address end-of-life consideration with the same diligence and foresight applied to its design and functionality. So first of all, the disassembly and recycling. With its compact and efficient structure, the SMPS design should be designed with ease of disassembly in mind. Components should be easily detachable, promoting efficient recycling process. Second, material selection and environmental impact. Considering the eco-friendly component highlighted in the design phase, it is essential to ensure that these materials maintain their sustainability throughout the product life cycle. Biodegradable or recyclable materials should be prioritized in the beneficial process, contributing to reduced waste and environmental impact. The careful selection of material can also mitigate potential hazards associated with certain components such as lead or other harmful substances. So, life cycle assessment or LCA. LCA is crucial to understand the environmental impact of the SMPS designing from its creation to disposal. This will include the extraction of raw material, manufacturing process, energy consumption, transportation uses, and eventual disposal. Next, the implementation strategy. The successful implementation of a sustainable SMPS design requires a carefully crafted strategy that addresses various aspects from a production to end-of-life disposal. Firstly, collaboration with recycling facilities. Building partnerships with recycling centers ensures that the components of the SMPS are treated by environmental regulation and best practices. Second, consumer education initiatives. Providing clear instruction on how to disassemble the SMPS units for recycling and offering information on local recycling facilities encourages users to actively contribute to the eco-friendly recycling life cycles of the product. Third, the take-back programs. Introducing take-back programs is a proactive approach to responsible waste management by allowing consumers to return obsolete SMPS units to manufacturers or design collection points. A closed-loop system is established. This is not only ensures proper disposal but also facilitates the recovery of valuable materials, promoting sustainability in the production cycle. Last but not least, the integration of circular economy principles. Embracing circular economy principles involves designing products with an emphasis on longevity, repairability, and recyclability. So, the cost-benefit analysis of implementing a sustainable SMPS design. So, first of all, the benefits. Firstly, the environmental conservation. By prioritizing eco-friendly materials and manufacturing processes, companies contribute to global sustainability efforts. This commitment to environmental conservation can result in enhanced CSR, which is corporate social responsibility rating, showcasing a dedication to principles beyond profit. Next, the regulatory compliance. Companies operating within the bounds of environmental regulation demonstrate a commitment to ethical business practices, earning trust and respect from stakeholders. Next is the customer trust. Building trust among customers who value eco-friendly practices is a significant intangible benefit. The positive perception of a company commitment to sustainability resonates with environmentally conscious consumers. However, the cost is the material cost. The initial investment in sustainable material contributes to a positive brand image and aligns with the growing consumer demand for environmentally responsible products. Over time, the positive association with sustainability can translate into increased market share and profitability. Last but not least, the recycling infrastructure. Establishing collaboration with recycling facilities and implementing take-back programs may involve additional costs in terms of logistics and infrastructure. Thank you.
For conclusion, Part 1, 2.1 highlight the significance of component selection in creating precise power supply circuit with multism. Part 2, 2.2 explore the switch mode power supply, offering efficiency and versatility. Despite switch mode power supply advantage like reduced heat, careful consideration is needed due to complexities and noise. Emphasizing sustainability, eco-friendly material, and proper disposal procedures minimize environmental impact, fostering a greener electrical future.